Welcome to The Explainer. Today, we're diving into one of the most powerful and most terrifying inventions in human history, the nuclear bomb. We're going to see how, in just a fraction of a second, it unleashes the power of a star right here on Earth. So how in the world do you generate a temperature that's hotter than the very center of the sun? Well, to get our heads around this almost unimaginable number, we have to start incredibly small. I'm talking about inside the atom itself. It all begins with the absolutely incredible amount of power that's locked away deep inside the nucleus of an atom. You see, nuclear weapons don't just create energy out of thin air. What they really do is convert a tiny, tiny amount of matter into a tremendous amount of energy. They're releasing the immense forces that hold that nucleus together, all thanks to Einstein's famous equation, E equals mc squared. The very first step to unlocking all that power is a process called fission. Now, think of it kind of like a perfect break shot in a game of pool. It all kicks off when a single free-roaming neutron slams into the nucleus of a heavy, unstable atom, something like uranium-235. So when that nucleus splits, boom, it releases a huge burst of energy. But, and this is the really crucial part, it also releases 2 or 3 new neutrons. Each one of those can then go on to smash into other uranium nuclei, creating this exponentially growing, self-sustaining chain reaction. And this all happens in mere picoseconds. We're talking trillionths of a second. It's unbelievably fast. Okay, so the physics is one thing, but the real engineering problem wasn't figuring out how to start the reaction. No, the real challenge was how to keep it from starting by accident, and then how to trigger it at the absolute perfect moment. This whole engineering puzzle really boils down to one single concept: critical mass. You can think of it as the tipping point. It's the absolute minimum amount of material you need for that chain reaction to keep itself going. And as you can see here, it's all about density. If the mass is subcritical, the atoms are too far apart. Too many of those neutrons just fly away, and the whole reaction just fizzles out. But once you make that mass supercritical by squishing it together really fast, the neutrons get trapped and that chain reaction goes explosive. So the whole trick is to keep the fuel subcritical until the exact instant you want it to go boom. So, faced with this massive challenge, the scientists on the Manhattan Project actually developed 2 totally different but equally brilliant ways to achieve a supercritical mass. Okay, so the first method is actually pretty simple in concept. It's called the gun-type assembly, and this was the design used in the little boy bomb that was detonated over Hiroshima. And it works pretty much exactly like it sounds. You use a conventional explosive, something like cordite, to fire a subcritical bullet of highly enriched uranium down a barrel. At the other end is a subcritical target made of the same stuff. The 2 pieces slam together, they form a supercritical mass, and then a little neutron initiator kicks off the whole explosive chain reaction. Now, that gun method was clever, for sure, but it was just too slow for plutonium, which is an even more potent and unstable nuclear fuel. To make that work, scientists had to invent a completely new and way more sophisticated design: the implosion method. This design, which was used in the Fat Man bomb, takes a completely different approach. Instead of shooting 2 pieces together, it starts with a single, subcritical sphere of plutonium. This sphere is then surrounded by these meticulously shaped high explosives, and when they detonate, they create a perfectly symmetrical shockwave that rushes inward. That crushing force is so immense, it violently squeezes the plutonium, making it so dense that it's forced to go supercritical almost instantly. So if you put them side by side, you can really see the trade-offs. The gun type is simpler, yeah, but its uranium fuel is actually pretty inefficient. Only about 1.5% of it actually fissions. The implosion-type, on the other hand, is way more complex to build, but it can use plutonium and is over 10 times more efficient. But hey, even 17% efficiency was just the beginning. The next giant leap in destructive power didn't come from splitting atoms apart, but from forcing them together by harnessing the exact same process that powers our sun. And this, right here, is nuclear fusion. At ridiculously high temperatures, light elements like hydrogen isotopes can be forced to fuse together. This forms a heavier element and in the process releases even more energy per atom than fission does. This is the science behind what we call thermonuclear weapons, or as you probably know them, hydrogen bombs. So the big problem was how on earth you create sun-like temperatures to get this fusion party started. Well, the breakthrough idea, known as the Teller-Ulam design, was both brilliant and, frankly, terrifying. You use a fission bomb as a match. Okay, so this is a multi-stage device, kind of like a Rube Goldberg machine of destruction. First, a primary fission bomb detonates, but it's not the blast we care about right now. It's the massive flood of X-rays it releases. Those X-rays are then channeled to a totally separate secondary stage that has the fusion fuel. The radiation instantly vaporizes the outer layer of this secondary stage, which creates this unbelievable inward pressure that just crushes and heats the fusion fuel inside. And then finally, a plutonium spark plug at the very center fissions, providing that final burst of extreme heat needed to ignite a massive fusion reaction. So what does this all look like when it actually happens? Well, the entire process, from start to finish, takes place on a timescale that is just, well, it's almost impossible to wrap your head around. From that initial fission trigger to the final enormous energy release from the fusion stage, the entire show is over in about 600 nanoseconds. That's 600 times billionth of a second. Just poof. So where does all that insane energy go? Well, about half of it becomes the physical blast wave. Another 35% is released as intense thermal radiation, just pure heat. And the rest of it? That becomes nuclear radiation, both the immediate pulse and the lingering fallout. That incredible release of energy instantly vaporizes all the bomb materials into a ball of plasma that's tens of millions of degrees hot. This is the birth of the fireball, which then expands incredibly rapidly, creating the shockwave and that iconic mushroom cloud as it rises up into the atmosphere. And of course, this isn't just some abstract science lesson. All this complex physics and incredible engineering, it has a devastatingly real consequence, one that changed the course of human history and the very nature of war itself. So we've gone from a single neutron to a city-leveling explosion in less than a millionth of a second. It's a journey of absolutely incredible scientific achievement, and it leaves us all with the most important question there is. Now that we've unlocked this fundamental force of the universe, what is our responsibility in wielding it?